This paper presents a new approach for task-driven design optimization of fingertip cutaneous haptic devices. Given one or more target tactile interactions to render and a cutaneous device to optimize, we evaluate the minimum number and best configuration of the device's actuators to minimize the estimated haptic rendering error. The 3 degrees of freedom device is composed of a static platform that houses 3 servomotors above the user's fingernail and a mobile platform that applies the requested stimuli to the fingertip. 3 cables connect the 2 platforms. By controlling the cable lengths, the motor can orient and translate the mobile platform in 3-dimensional space. The 6 degrees of freedom device is a parallel continuum manipulator, consisting of 6 parallel compliant legs that pass through a fixed base platform and attach to the distal platform. The end effector's pose can be controlled by independently adjusting the 6 leg lengths via 6 motors behind the base platform. We considered 6 tactile experiences recorded during 6 different interactions between a stationary BioTac sensor and a flat metal surface that was moved by hand to touch the BioTac's fingertip in different ways. First, we calculate the motion needed for the original cutaneous device to render the considered target interaction. Then, we run a principal component analysis to search for possible couplings between the original motor inputs, looking also for the best way to reconfigure them. If some couplings exist, we can redesign our cutaneous device with fewer motors, optimally configured to render the target tactile sensation. The flat interaction requires only one principal component to be rendered correctly by our device. This means that we could design a new cutaneous device with only one motor, and the coefficient of the first principal component can tell us how each cable should move relative to the motor. Here we show a possible design for this optimized device that weighs 54% less than the original 3DOF version. The tip-flat tip interaction requires at least 2 principal components to be rendered correctly by our device. As before, this means that we could design a new cutaneous device with only 2 motors. Here we show a possible design for this optimized device that weighs 15% less than the original 3DOF version.